I will record this class also. Okay. Okay. In last class, we discussed about antenna and its parameters, few parameters. So in that class, we discussed about first one, radiation pattern parameter discussed. And second one, we have discussed the radiation intensity represented by U. And third one is gain. In that gain, we discussed directive gain, power gain. And fourth one is what? Antenna efficiency or efficiency factor of the antenna. So that is neta. Of course, here radiation intensity is defined as what? Radiated power per unit solid angle. As this angle changes, the radiated power through that solid angle also changes. Radiation pattern is what? Graphical representation. It is a graph of radiation from the antenna. Graph of radiation from the antenna. And gain, directive gain, power gain. So here only W are considered in the definition. Here loss also considered means total power, where WT is equal to what? WR plus WL. The definition of gain is what? Radiation intensity from the test antenna or practical antenna to the radiation intensity from the reference antenna or isotropic antenna. Isotropic antenna means what? An antenna which radiates energy uniformly in all directions. Coming to the antenna efficiency, it is defined as a radiated power, ratio of radiated power to the total input power given to the antenna. It is given by what? RR by RR plus RL. And this neta can be written in terms of what? GP by GD. GP by GD. It implies that what? GP equal to GD. Neta equal to what? 1. That means efficiency factor is 1. Efficiency percentage is 100%. Means if GP equal to GD means what? WT equal to WR. That means radiated power is equal to what? Total input power. That means whatever the power given to the antenna, that power is radiated into the space. That means it gives 100% efficiency. These parameters discussed in the previous class. Now we will discuss another parameter, that is directivity. Before discussing about directivity, we need to discuss about the beam area. Beam area is represented by omega suffix A. This omega indicates what? Beam solid angle, and A indicates what? Area. So that's why this omega suffix A indicates what? Beam area. Beam area is nothing but what? Beams are nothing but the lobes. What are the lobes we have? Major lobe and minor lobe. These lobes indicates what? Radiation from the antenna. So that's why total beam area is what? Sum of the minor lobe area and major lobe area. So this omega suffix M indicates what? Minor lobe area. And this one indicates what? Major lobe area. From this, we can define another parameter, that is beam efficiency. Let us divide this equation with omega A on both sides. You will get what? Omega A by omega A equal to 1. And here you will get what? Small omega M divided by total, that is beam area. Here major lobe area divided by total beam area. So this one is known as what? Beam efficiency, because major lobe indicates what? It indicates the direction of maximum radiation in the desired. It indicates the direction of the maximum radiation in the desired direction. So that's why it is known as what? Beam efficiency. Beam efficiency. And here this one is known as what? Stray factor. This one is known as what? Stray factor. It is defined as what? Ratio of the minor lobe area to the total beam area. This one is desired one, and this one is undesired one. This is the desired one. and this one is undesired one. That undesired one is known as what? Stray factor. Beam efficiency definition is what? Beam efficiency, I am writing BE. BE means beam efficiency. It is defined as ratio of the major lobe area to the total beam area. So this one is beam efficiency. Beam area is over and beam efficiency over. And beam area is also written in equation form like this also. Beam area is equal to integral of the normalized power over a solid angle. Integral of the normalized power over a solid angle, or else normalized function, because this normalized power or normalized function doesn't have any units. That is Fn. Fn, where Fn is equal to Fn or Pn. Pn means what? Normalized power. Pn means normalized power. It is given by P by P max. P by P max. Similarly, Fn given by what? F by F max. The units of F and F max are same, so there are no units. So, but beam area has units. So, beam area has units. So, that is nothing but what? Units of the solid angle. Okay. So, therefore, here beam area that omega A can be written as what? Integral of the normalized function over a solid angle. Over a solid angle, where Fn equal to F by F max. From this, we can define another parameter, that is directivity. Directivity of the antenna. Directivity of the antenna. It is represented by D. It is represented by D. So now here we can write this D definition is nothing but what? GD max. GD max means what? Already we have the definition of the GD. That is what? GD is nothing but directive gain. It is defined as what? Radiation intensity from the test antenna, to radiation intensity from isotropic antenna. Radiation intensity. RI indicates what? Radiation intensity from isotropic antenna or reference antenna. Isotropic antenna is taken as what? Reference antenna. Isotropic antenna means what? An antenna which radiates energy uniformly in all directions. For test antenna, radiation intensity is given by, that is U, and radiation intensity from the isotropic antenna, as it radiates energy uniformly in all directions, that uniform value is taken as what? Average value, that is average value of the radiation intensity. Now we can write this U as what? That is U equal to what? U equal to WR is equal to integral radiated power per unit solid angle. So this U can be written U, this one U, and U average is what? WR by 4 pi. Now we can write this directivity as what? 4 pi into U divided by WR. I forgot to write one thing. What is that? D equal to what? GD max. But this one is what? Definition of the, this entire thing is what? Definition of the GD only. So maximum means what? It should be maximum. Numerator should be maximum. This value should be maximum. When it maximum, here you have the numerator and the denominator. When numerator becomes the maximum, then only you will get the U max. Here also U max. This 4 pi U max divided by WR. But we have WR. What is WR? WR is equal to what is WR? WR is equal to integral U d omega. But we have already D is equal to what? 4 pi into U. U is U max. And here WR, the WR, I am writing, substituting WR. WR is equal to what? Integral U d omega. Then it can be written as what? 4 pi integral, as U max is the constant. It can be written outside of the integration or inside the integration. Then there is no change. You can write this one as u by u max. If you send this part into the denominator, it becomes what? U by u max into d omega. You have what? This 4 pi. This is nothing but what? Normalized function only, or normalized value. 4 pi integral fn d omega, that equal to what? 4 pi omega a. That is d. D is equal to 4 pi by omega a. This is the relationship between directivity and beam area. Relationship between directivity and beam area. Directivity and beam area. It clearly shows that directivity is inversely proportional to what? Beam area. Beam area. As area is narrow, directivity is more. As an area is wide, directivity is less. So this is about the relationship between the directivity and beam area and parameter of the directivity. What is directivity? Directivity is nothing but the maximum directive gain. Already you have the definition of gain, that is radiation intensity from test antenna to the ratio of the radiation intensity from the test antenna to the radiation intensity from isotropic antenna. It can be written as what? U max by U average, because numerator should be maximum in order to get this GD as maximum. And in the denominator, for isotropic antenna, radiation intensity taken as what? U average. That U average can be written as what? WR by 4 pi. It can be written as what? 4 pi into U max divided by WR. In the next step, we substituted WR. The WR is what? In terms of U, integral U d omega. And finally, we can write this as what? 4 pi by integral U by U max d omega. U by U max is taken as what? Normalized function. You know, integral of the normalized function over a solid angle is what? Beam area. So that's why d equal to what? 4 pi by omega a. It is clearly telling that the directivity is inversely proportional to the beam area. So this is about the directivity. Next, as we discussed about the beam area, we need to discuss about what? Beam width. Beam width. So there are two types of the beam widths. One is off power beam width, and another one is beam width between first nulls. So HPBW. HP indicates what? Off power, and this BW indicates what? Beam width, not bandwidth. And another one is first null beam width, or else beam width between first nulls also. It is also studied as what? Beam width between first nulls. Off power beam width, name itself, it is the beam width measured at the off power points. And beam width between first nulls, name itself, it is measured between the first null points. Null means what? 0. Okay, actually antenna radiates the maximum energy in a particular direction, minimum or less in other directions. Now let us take major lobe for the antenna. So as like this. So this is the major lobe. I assumed that antenna placed here radiates maximum energy in this direction. So that is represented by major lobe. So this is the major lobe. This is the major lobe. And let us take minor lobes also, like this. Okay, nulls in this direction. Assume in this direction there is no radiation. So these are the nulls. Off power beam width means, so let us represent this one with off power beam width with red color. So off power beam width, it is the angular width measured on the major lobe. It is angular width measured on the major lobe between 2 points, 2 off power points, P1 and P2. These P1, P2 are the off power points. P1 and P2 are the off power points. Here we have some angular width. So this angular width, we have angular width. This angular width is nothing but what? Off power beam width. Off power beam width means, what is the definition of the off power beam width? It is an angular width measured on the major lobe between 2 off power points. What is meant by half power point? It is the point where power is equal to the half of its maximum value. Power is equal to what? Power becomes what? Half of its maximum value. Half of maximum value. And as power is half of maximum value, half of its maximum value. And what about the field? Field obviously equal to what? 1 by root 2 of its maximum value. 1 by root 2 of its maximum value. That means at P1, P2 points, power is equal to half of its maximum value. Let us say maximum is P max, half of its maximum value. And field is equal to what? 1 by root 2 of its maximum value. As field is equal to the 1 by root 2 of its maximum value, this half power beam width is also known as what? 3 dB beam width. It is also known as what? 3 dB beam width. So this is about what? Beam width. Suppose if you want to determine the half power beam width for the given radiation intensity, that is, let us say it is theta. Okay, no? So you need to determine this theta. Okay, for this you have to determine this theta for this point. At this point, let us say radiation intensity is sin theta. Radiation intensity is given by what? Sin theta. Radiation intensity means what? Radiated power per unit solid angle. And it is equal to what? At half power points, at P1, it is equal to what? Half of its maximum value. Half of its maximum. What is the maximum value of sin theta? 1. Okay, so therefore, P1, that means power. At a P1, power is equal to what? U is equal to what? 1 by 2 of 1. Or power equal to 1 by 2 of 1. So therefore, here, that given component is what? Sin theta. Sin theta equal to what? 1 by 2. So therefore, theta value is what? 30 degrees. So this is 30 degrees. And here also you have what? Adding this theta plus theta gives what? Total angular width. That is what? 30 degrees plus half power beam width. In this case, half power beam width can be written as what? That is equal to half power beam width is equal to what? Theta plus theta. Gives what? 60 degrees. Like this, we can define nulls also. The beam width between first nulls also. Beam width between first nulls. Beam width between first nulls. So let us take beam width between first nulls. So that can be defined. Yeah. Angular width between first null points. Let us take these are the first null points. Let us take Q1 and Q2. Okay, small Q1 and Q2. Q1 and Q2. So this is the angular width. Year to year, some angle that is, let us say it is some theta 1. And here also I have what? Another theta 1. Theta 1 plus theta 1 gives what? Beam width between first nulls. Because it is measured between the null points. Null points. So now I am taking radiation intensity is given as U is equal to, in the previous case I have considered sin theta. Now I have taken cos theta. Radiation intensity is like this. So then determine the beam width between first nulls. First you have to determine what? Theta 1. For this theta 1, U should be equal to what? U should be equal to what? U minimum. That means it becomes a 0. So that is cos theta value, minimum value is 0. Theta 1 means at the, at theta 1. Or else for theta 1, U minimum, you will get U becomes what? U minimum, that equal to what? 0. Therefore, this cos theta is equal to what? At theta equal to theta 1, cos theta 1 equal to 0. Then theta 1 value is what? 90 degrees. So therefore, theta 1 plus theta 1 gives what? Beam width between first nulls. So therefore, 90 plus 90 gives 180 degrees. This one is what? Beam width between first nulls. So now we successfully discussed about beam width, half power beam width and beam width between first nulls. Very simple. Half power beam width means what? It is an angular width measured on the major lobe between two half power points. And beam width between first null points means what? Beam width between first nulls means what? It is an angular width measured at the first nulls, between first nulls. Null means what? 0. As it is 0, radiation or radiated power or radiation intensity becomes what? 0 at these points. By making radiation intensity equal to 0, we can determine what? Beam width between first nulls. By making radiation intensity equal to half of its maximum value, we can find what? Half power beam width. Next, other parameters. other parameters. So effective aperture, effective aperture, effective aperture, effective aperture. Aperture means area. Aperture means area, that is represented by A. As it is effective aperture, it is represented by AE. Actually, already I told that aperture means what? Area. It is defined as what? Ratio of the power received at the load terminal of the antenna to the pointing vector of the incident wave. That means this terminology is related to what? Receiving antenna. Power received. W suffix R indicates what? Received power. Whereas W suffix small r indicates what? Radiated power. Don't confuse. And P is what? Pointing vector. So this is nothing but what? Effective aperture. So if you see the units, what are the units of power? Received power, that is measured in terms of watts. Pointing vector, you know about pointing vector, that is nothing but what? Power density, that is watts per meter square. Watts gets cancelled. It is equivalent to what? It gives meter square only. That means the units of area is nothing but meter square. So that's why it is known as what? Effective aperture. There is a relationship between gain and directivity and this effective aperture. So first I will write this directive gain, that is GD. GD is equal to what? 4 pi by lambda square into AE. This is the relationship between the directive gain. Directive gain. As you know, directive gain, maximum directive gain is nothing but directivity. So that's why D is equal to what? GD max. At the given frequency, this lambda is fixed or constant. This 4 pi is also constant. In order to get GD as maximum, AE should be max. So that's why here we have to take right, or else we can write D as what? 4 pi by lambda square. At a given frequency, this lambda is constant, this one is constant. In order to get to this GD as maximum, we need to make this AE as maximum, that is AE max. This is the relationship between directivity and maximum effective aperture. This is the relationship between gain and effective aperture. So this is about effective aperture. And another parameter, that is effective height. Effective height or effective length. Effective height or effective length, that is represented by HE or else length, effective length or effective height, LE. It is defined as the ratio of the electric field intensity of the incident wave to the induced voltage in the antenna. The units of this one is what? Volts per meter electric field intensity, and the unit of voltage is what? Volts. So volts cancel. Actually, it is okay. I told in a reverse manner. Actually, sorry. It is defined as what? A ratio of the induced voltage in the antenna to the electric field intensity of the incident wave. The units of V is what? Volts. And the units of E is what? Volts per meter. So here volts gets cancelled. 1 divided by per meter gives what? Units are meter. So length or height is measured in terms of the meters. It is defined as what? Ratio of the induced voltage in the antenna to the electric field intensity of the incident wave. Actually, this effective height is different for different current distributions. If there is a linear current distribution, this effective height LE is equal to LPHY divided by 2. This LPHY indicates what? Physical length of the antenna. And this is for what? Linear current distribution. And for sinusoidal current distribution, LE for sinusoidal current distribution, LE is equivalent to 2 into LPHY divided by pi. So this is for sinusoidal current distribution. This sinusoidal current distribution is observed for the quarter wave monopole antenna and half wave dipole antennas. Quarter wave monopole antenna means what? Lambda by 4 antenna. The length of the antenna is lambda by 4. So the type of antenna is known as what? Quarter wave monopole antenna. So this one is known as what? As length is equal to half of the wavelength. So this one is known as what? Half wave dipole antenna. So these are the different wire antennas. One is quarter wave monopole antenna, quarter wave monopole antenna, and another one is what? Half wave dipole antenna. Half wave dipole antenna. Okay. So please remember these values. And if there is a uniform current distribution, effect physical length. Uniform current distribution is possible if length of the antenna is very small. Here it is for what? If length is small and here length is very small. Length of the antenna is very small. And here length is considerable in terms of what? Lambda. That is lambda by 4 and lambda by 2 antennas. Please remember these formulas. Because we have the radiation resistance formula for the edge and dipole antenna. For a edge and dipole antenna means what? Edge and dipole antenna. In addition to quarter wave monopole antenna and half wave dipole antenna, we have edge dipole antenna or else edge and dipole antenna. Edge and dipole antenna, or it is also known as a very small electric dipole antenna. Very small means what? The length of the antenna is negligible. Length of the antenna is very small when compared to the lambda. So in this case, the radiation resistance of the edge and dipole antenna is given by 85 C L by lambda whole square. L by lambda whole square. Okay. So this is for what? If length is negligible. If length is very small, already I told. And for quarter wave monopole antenna, RR equal to what? 36.5 ohms. And for half wave dipole antenna, it is 73 ohms. So here length is equal to lambda by 2 antenna. And here length of the antenna is what? Lambda by 4. So please remember these values. Okay, of course we have derivation. I will share this derivation separately. Okay. In today's class, what we have discussed? Okay, we will see. First, okay, that is the revision of the class. And then after, beam area, that is total, it is sum of the minor lobe area and the major lobe area. From that, we defined beam efficiency. Beam efficiency is defined as what? Ratio of the minor lobe area to the total beam area, and this factor is what? A stray factor. Okay. Next, here normalized function. Beam area can be written in terms of the normalized function. Here normalized power can be written as what? P by P max. It is unitless quantity, and Fn is what? Unitless parameter. Fn equal to what? F by F max. So therefore, omega A is equal to what? Integral Fn d omega. Means beam area is equal to what? Integral of the normalized function over a solid angle. From that, we can derive relationship between directivity and beam area. Directivity equal to what? D equal to GD max. Already we have the definition of the GD. Just we need to maximize this one. As you have numerator and denominator, in order to get the maximum value, we need to maximize the numerator. That means U by U average. In order to maximize this D, you need to maximize U max. So finally, we got D as what? 4 pi by omega A. Then we discussed about beam width, half power beam width, first null beam width. Beam width means angular width. Measured between two half power points, that is half power beam width. Measured between first null points, that is beam width between first nulls. Please remember, at half power points, radiation intensity equal to the half of its maximum value. Radiated power equal to half of its maximum value. Field equal to what? 1 by root of its maximum value. At first null points, null means what? 0. So at first null points, power is equal to what? 0. And radiation intensity is also 0. Field is also 0. So from this we determined the half power beam width and next we defined effective aperture and effective height. Effective aperture is nothing but what? It is defined as the power received at the load terminal to the pointing vector of the incident wave. There is a relationship between gain and directivity in terms of effective aperture. In terms of effective aperture, GD equal to 4 pi by lambda square AE. And similarly, we know about D equal to GD max. As GD is 4 pi by lambda square AE, D equal to what? 4 pi by lambda square AE max. Then after we discussed about the effective length or height. It is defined as what? Ratio of the induced voltage in the antenna to the induced voltage in the antenna due to the incident wave. To the ratio of the electric field intensity of the incident wave, we have the units of a meter. So we have different current distributions for different antennas. Small, we have linear current distribution. In case of the linear current distribution, effective length is equal to what? Physical length by 2. In case of the sinusoidal current distribution, this sinusoidal current distribution can be found in the quarter wave monopole antenna and half wave dipole antenna. So for that, L is equal to what? 2 into L. And in case of the very small antenna, that means if the length is very small, in that case, we have the uniform current distribution. As current is uniform, that means the length is also very small. In that case, L equal to what? L physical. That means effective length and physical length both are same. For a like this, and for quarter wave monopole antenna, radiation resistance equal to 36.5 ohms, and for half wave dipole antenna, radiation resistance is 73 ohms. Half wave dipole means what? Length is equal to half of the wavelength, and quarter wave monopole antenna means what? That is length is equal to quarter of the wavelength. Okay, and we need to discuss one important relationship between the Poynting vector and radiation intensity. So Poynting P and Poynting vector is represented by P. Average means what? Average Poynting vector, pi or u. Okay, so actually we know the definition of the relationship between P average and U. We know about U, radiation intensity. It is defined as what? Radiated power per unit solid angle. That is, as this solid angle changes, radiated power through that solid angle also changes. From this, we have WR is equal to what? Integral U d omega. U d omega. But radiated power, in the Poynting vector theorem, we discussed about this one. Radiated power can be calculated by using the P average, that is integral P average dot ds. So you can see this one is the equation 1 and equation 2. Both are same. So therefore, we can write this integral U d omega U d omega P average, as it is average, it is constant, we can write outside of the integration, integral ds sin theta d theta d pi. We can write it implies u integral U d omega P average. So integration with respect to theta and pi. So we can write this r square outside of the integration because there is no integration with respect to sin theta d theta d pi. There is no integration with respect to r. And we can write this as the P average into r square. Integral d omega. Integral. Yeah, this integral d omega cancel. Okay. So therefore, U can be written as what? U is equal to what? Hence, you can write U as what? P average into R square. P average is what? Average Poynting vector or average power density. This is the relationship between radiation intensity and Poynting vector. Okay. So in today's class, we discussed the maximum all the parameters of the antenna and relationship between the P average and U, and relationship between the directivity and effective aperture. Okay. Okay, here I am stopping today's class. We will meet in next class. In next class, we will discuss about the rectangular waveguides.